What if I told you that this robot arm started as a simple scripted movement and is now able to see, decide, and act on its own? In this video, I'm going to walk you through how we got here, step by step, including all the problems we ran into and the key breakthroughs that made everything finally work. At the very beginning, this project was extremely simple. We had a robotic arm in a simulation and a cube placed in front of it. The robot could move, but only because we were telling it exactly what to do. Every position was hard-coded. Every movement was predefined. It had no awareness of its environment. It worked, but it wasn't intelligent. We were using PyBullet, which is a physics simulation engine. That means everything you see, gravity, collisions, friction, is being simulated in real time. So this isn't just animation. This is a virtual environment that behaves like the real world. The robot itself is a model of the Franka Panda arm, which is an actual robotic arm used in research and industry. In our case, it's loaded from a URDF file, which defines all its joints, links, and physical properties. So we're essentially controlling a digital version of a real robot. Our first goal was simple. Pick up a cube and move it somewhere else, but this is where things got interesting. The robot would miss the cube or grab it from the wrong angle. Sometimes the cube would roll away. Other times the gripper would close, but nothing would happen. We had to fine-tune the positioning, adjust the inverse kinematics, and carefully control how the arm approached the object. Eventually we got it to pick up the cube, but then a new set of problems appeared. As soon as we relied more on physics, things became unstable. The cube would dangle from the gripper. It would rotate randomly in the air. Sometimes it would even get thrown when released, and in some cases the cube would snap into the gripper from a distance, which made no physical sense. At that point, it became clear that pure physics-based grasping in simulation is extremely difficult to control. That's when we made a key decision that changed everything. Instead of trying to simulate a perfect physical grasp, we switched to a kinematic approach. In simple terms, when the robot grabs a cube, we temporarily take control of the cube's position directly. We attach it to the gripper in a controlled way so it follows the robot perfectly. Then, when we release it, we restore physics. This completely eliminated the instability. No more dangling, no more rotation, no more unpredictable behavior. The robot suddenly became precise and reliable. Once the grasping was stable, we moved on to the next big step, vision. We mounted a virtual camera on the robot's wrist. Now the robot could actually see the environment. It could capture images, detect cubes based on their color, and identify their position in the camera view. This was a major shift. We were no longer telling the robot where the cubes were. The robot was figuring it out on its own. From there, we implemented a feedback loop so the robot could align itself with a cube. It looks at the image, finds the cube, compares its position to the center of the screen, and then adjusts its movement. This technique is called visual servoing. Now the robot could move toward objects without knowing their coordinates ahead of time. Once we combined vision, alignment, grasping, and movement, we had the foundation for a fully autonomous system. The robot can now scan the environment, find a cube, move toward it, pick it up, and place it somewhere else, all in a continuous loop. We also added a simple decision layer based on color. Of course, getting to this point required solving many small but important issues. For example, we introduced a scan position, a neutral position above the scene, where the robot always returns before searching again. That one change made the system much more robust. What we have now is not just a script, it's a complete loop: perception, alignment, action, and recovery. And that brings us to the next step. Right now, the robot follows a predefined logic. But what if it could decide what to do on its own? In the next phase, we're going to integrate HRM decision-making. The goal is to allow the robot to observe its environment and choose actions dynamically. Instead of telling it exactly what to do, we'll let it figure out the details. This is where things move from automation to intelligence. If you've been following along, you've just seen how a simple robotic simulation can evolve into an autonomous system. And we're just getting started. I'll see you in the next video.